Hello everyone. In today's video I will be showing you how I made a flocking algorithm in Unity. Now before we get started, let's start with a breakdown on what a flocking algorithm is. A flocking algorithm is an algorithm in which you can simulate large crowd-like behaviors to move as a crowd without it feeling too mechanical and more organic, like they're not moving too close together, they feel real, like a bird moving in a flock. You see this all the time in video games when they simulate large crowd-like behaviors, and I tried to do a scaled-down version like that in Unity. Let's get started. When we run the scene, you see we have our flock of 50, or boids, over here, starting at their first waypoint. They'll be trying to get to this blue box over here, their second waypoint. However, two obstacles stand in their way. Luckily, this flocking algorithm comes with obstacle detection. Let's see it in action. You can see at the start of the scene, all the balls will come together at a flock and move to the right. They have an obstacle vector which tells them to go around this obstacle. However, this next obstacle makes it more interesting. They all don't go in the same direction. As you can see, some are going to the left, some went over, and some decided to be cheeky and go under. All of them made it through the obstacle, but they did it in different ways. Thus, keeping it a very organic way of movement. As you can see, the flock is spread out, but not to worry, all their speeds are different. Like this lone guy who got stuck in the back, he moves faster than the others because he doesn't have many neighbors, so he'll catch up. And here we can see all the balls avoid the obstacle again, and now they're coming back to their next waypoint. Now, how does this work? The flocking algorithm is the series of adding vectors, such as a cohesion vector, how close should the balls move together, an alignment vector, how far away should they be so that they're not too mushed together, an alignment vector, how should they align, and an obstacle vector, how should they avoid obstacles. I also added a waypoint vector for them to be able to move from waypoint to waypoint efficiently. These vectors are multiplied by weights. Where can we see the weights? On the flock itself. You can manipulate the whole flocking behavior just by manipulating the cohesion. You don't want them to be too close together. You can either decrease the cohesion weight or increase the avoidance weight, making the flock more spread out. If you wanted them to align better, you would increase the alignment weight. All of these can manipulate the object in different ways. But let's go into how it actually works. The way it works is that we have our cohesion vector, our avoidance vector, our alignment vector, and our obstacle vector. You can't see it now, but there's also a waypoint vector, and we all added to our move vector. I added these custom weights just because I thought that was best for my program. You can add whatever you want. We then smooth damp our move vector with our transformed out forward in terms of our current velocity. We normalize it, and then we manipulate our position and forward based on that move vector. To calculate speed, we first calculate our neighbors. If our cohesion neighbors are based on the number of cohesion neighbors that we have, we take their speed, and then we divide it by our speed. And then we clamp it between our assigned flock min speed and our assigned flock max speed, basically saying that the more neighbors you have, the slower you move, allowing you to stay in a flock. How do we find our neighbors? Well, the way we do it is that we take our current neighbor, we find the turn distance from one unit to all the other units around it, and we check to see if that distance squared is less than our cohesion distance, our avoidance distance, and our alignment distance squared. How do we know this? Well, if we go back to Unity, you can manipulate those distances as well. So basically, by manipulating these distances, you manipulate how many neighbors are in the scene, and thus you can manipulate the size of the flock, the speed at which they move, and how spread out they are. I think personally that's really cool. How do we calculate our cohesion vector? Well, what we do is that we find all the cohesion neighbors, or at least those that are in the FOV. We do that by finding the vector 3 angle between our forward position and is it less than our FOV angle. I believe my custom FOV angle is something like 270 degrees. If it is, we add it. We add it to our neighbor's FOV, and we add that position to our cohesion vector. Once we get our jumbo-sized cohesion vector, we divide it by the number of neighbors in our FOV, and we subtract it from our position. We then normalize the cohesion vector and return it. We do the same thing for alignment vector and avoidance vectors, only we don't subtract it from our position because unlike the alignment vector and the cohesion vector, unlike the alignment vector and the avoidance vector, the cohesion vector depends a lot on position because it's about that ball's neighbors. The avoidance vector and the alignment vector, not so much. The obstacle vector is where things get interesting. The obstacle vector, well, the first thing we need to do is decide what are obstacles. We do that by inputting an obstacle mask. If we go back to Unity, we can see that the obstacles that we have here are under a layer called obstacle. And if we go to our void, they have an obstacle mask that they have specifically been told to avoid. We use physics raycasting, basically raycasting in 4 directions, up, left, right, and down, to see does our raycast hit the obstacle. If it does, we make an obstacle vector and we set it to our next function, which is finding the best direction to avoid an obstacle. There are 2 ways we do this. We raycast in the 4 directions again, and we only at a further radius, and we see, okay, does it hit anything? Does it hit an obstacle? If it doesn't, then we go in that direction because we've avoided the obstacle. If it hits the obstacle in all 4 directions, then we pick the direction that takes the longest amount of time, because by the time we reach closer to that obstacle, we would have probably found another vector in which we can move to avoid the obstacle. As you can see here, if it doesn't hit, then we return it. If it does, if all 4 hit, then we set our current direction is equal to our transform.transform direction, and we move in that direction. We set our selected direction to current direction if our current distance is greater than our max distance, and then we normalize our selected direction and return it. These 2 functions are just for following our waypoints. I just make a direction between our waypoint position and our position in the waypoint position, and then this is how I find the next waypoint, so it goes back and forth. The way we initialize our flock is that we set up our spawn setup. So if we go back to Unity and come to our flock, this will be our void flock that will be multiplying. We want a flock size of 50. And you can see here that we'll have a spawn bound around this cube of 10 in the X, 5 in the Y, and 10 in the Z. We have our cohesion distance, we have our vector distances, our speed, and our vector weights. Once having that, we generate our units by saying for every unit, we want a random vector inside the Unity engine sphere. We want it in terms of the spawn bounds. And then we manipulate our spawn position based on the random vector, and then we instantiate it at that spawn position with a random rotation. And then we initialize our speed to be the average of the min speed and the max speed. Overall, that is how you make a flocking algorithm in Unity. You find all the vectors that you need, you add them up, and you normalize them. And if you want to be cool, you can manipulate this. Like if I was to reduce the cohesion vector, you can see that they are spreading out and becoming a lot bigger and farther away from each other. And I think that's just a great add-on. So that's how I did it, and I hope you enjoyed.